Hello everyone. This study is about the conductive properties of cation exchange membranes. Cation exchange membranes are the ion exchange materials which have negatively charged fixed groups such as sulfate, phosphate, carbonate, etc. in their membrane backbone, which allow the flow of oppositely charged cations, but anions are blocked due to the electrostatic repulsion. As you can see in figure 1, the cations are easily able to pass through the cation exchange membranes while the anions are blocked due to electrostatic repulsion. Since cation exchange membranes are capable of transporting cations between the electrodes, they are widely used in several electrochemical processes such as redox flow batteries, water electrolysis, fuel cells, etc. These commercial membranes are mostly used in fuel cells. The conductivity of these membranes has a significant role in the efficiency of fuel cells. These fuel cells have lower or even zero emission compared to that of combustion engines. Most of the literature available today provides the conductivity measurements of Nefian membranes, while some of them are based on Acubian membranes, which is also a perfluorosulfate. This study provides the results from the measurements of conductivity properties of 15 cation exchange membranes. Such properties include conductivity measurements, ion exchange capacity, and water absorption measurements by this cation exchange membrane. For conductivity measurements, the membranes were cut into rectangular pieces and boiled in 10% nitric acid for pretreatments, as you can see in figure 2. Then two different types of conductivity measurements were carried out. As you can see in figure 3a and figure 3b, they represent the circuit arrangement for normal conductivity and tangential conductivity measurements respectively. For normal conductivity measurements, through plane measurements were done, while along the plane measurements were done for tangential conductivity measurements. For ion exchange capacity measurements, membranes were first regenerated to hydrogen form using zero point 0.1 molar sulfuric acid, followed by titrating them with 1 millimolar sodium carbonate. For water absorption measurements, the membranes were dried in vacuum at minus 13.5 psi at 1775 degrees Celsius overnight, and the dry and wet mass of membranes were used for calculation. Figure 4 shows the tangential conductivity measurements of cation exchange membranes, where Nefian 117 had the highest tangential conductivity value and Nefian 211 had the lowest conductivity value. Figure 5 shows the ion exchange capacity measurements of all these ion exchange membranes, and figure 6 shows the water absorption by cation exchange membranes, where one of the fumapam membranes had the highest water absorption value. To conclude, I would say improving the cost effectiveness of these fuel cells would help prevent the emission, as these fuel cells have relatively lower or even zero emission compared to conventional internal combustion engines. So using less expensive cation exchange membranes can be another alternative to reduce the cost of using fuel cells, and we can prevent the greenhouse gas emissions. Finally, I would like to thank NASA, National Science Foundation, and UTA for their support towards this study. Thank you.